All right. Hey, everybody. Last time before we parted ways, we discussed how to define and work with contour integrals. And so I've written down just the basic formula that you should know for the definition of a contour integral. So I have a contour C. That's a curve that's parameterized by a complex function of a real variable. So here's an example picture over here. Here's my curve C, and it's parameterized by some complex function of a real variable z of t. So you plug in real numbers t between a and b, and as you do that, you trace out c. And so we define contour integrals of complex functions over these contours c. And how do you do that? Well, it's actually really reminiscent of things we learned in Calculus 3. You plug in the parameterization z of t everywhere you see is z in f. So f of z of t, you multiply by z prime, and then you integrate from a to b. And so we're back to an integral of a complex function of a real variable, which we learned how to do, I believe, Wednesday before we parted ways. I didn't want to rework these examples, but I wanted to remind you of them because they're very important. So we worked out, using this definition, we worked out this example, the integral of 1 over z over the unit circle. This notation here is the circle of radius 1 centered at the origin. We got 2 pi, and we actually saw that this is actually just a special case of the general problem here, where you take the circle of any positive radius r. I guess I should mention that r is bigger than 0. Any positive radius r centered at z naught, you integrate 1 over z minus z naught dz. You parameterize the circle, you plug it in, you follow this, and you end up with 2 pi as well. We also showed that if you integrate z minus z naught to the n, where over the contour c, where c is circle radius r centered at z naught, then you actually get 0 whenever n is not equal to -1. So those are some of the examples that we did last time. I couldn't remember if we finished up going over just a couple of basic properties of contour integrals, so I thought I would do those in this first video, and then we'll move on to some other really interesting theorems. So let me write this down for you. So some properties of contour integrals. All right, so the first property is very intuitive. If I have a contour integral and I've got some constant z naught times f of z dz, you'd like to be able to pull the z naught out, and that's exactly what you can do. So no problem there. We actually saw this property when we looked at the definition of a complex, of the integral of a complex function of a real variable, and so that this particular property follows from that one. Second property that you'd really like to have with integrals is if I have the integral over a contour C of the sum of two functions, let's say f of z plus g of z, I'd really like to be able to break this up as the integral over c of f of z plus the integral over c of g of z, and it turns out that's exactly what you can do. We talked about this briefly in class, but you might wonder what happens if I change the orientation of c. Let me scroll up here. Here I've defined my parameterization of c starts me here and goes this way. What if I find a different parameterization that starts me at this point and goes the other way? How does that change the integral? Well, first off, we're going to denote the opposite orientation of c by minus c. So when I write down minus c, you know what I mean. So the integral over minus c of f of z dz, this is the backwards orientation. Well, this is just negative the integral over c of f of z dz. Now, the way that I've written this, it's not clear which orientation is the one that you're starting with. The point is, when you change the orientation, when you reverse the orientation, it just puts a negative on your integral. And then finally, we've talked about the need for these contours to be piecewise smooth. And so what happens if there's finally, I want to show you one more thing. So if you have two curves like this, maybe I've got this guy, and then I've got this guy. Here is C1, here is C2, and I'm going to think about C as the whole thing. So my C here is going to be the whole thing. Let me move that down. Actually, this isn't going to fit on this page. I want to be able to save this for later. So then the integral over the whole C of f of z dz, you can actually break this up as the integral over C1 of f of z dz plus the integral over C2 of f of z dz. And you can actually extend this process to any finite number of connected curves. All right, on we go. So we're going to be diving into section 44 through 49. The sections in the book are very small, and we're actually going to skip several of them or some long proofs. But at the end of this series of videos, we'll be ready for our first homework assignment, and I'll give you those problems. So I want to look at a theorem with you. This is just a really important theorem. We'll be looking at 2 or 3 theorems throughout. I've gone in and written it down to save a little time. So I'm starting with a continuous function on a domain D. Remind yourself what a domain is, right? Non-empty, open, connected set. And f of z is continuous. So then the following are equivalent. So 1, you have an antiderivative on D. And 2, given any 2 points in D in any path between those points, so C is just a path taking you from Z1 to Z2, then you can write your contour integral as the antiderivative at Z2 minus the antiderivative evaluated at Z1. And that's equivalent to, if you have a closed contour C lying in D, then the contour integral of f over C is actually just 0. And of course, you can see how 2 implies 3. Now, I want to make something very clear to you. This theorem is not saying 1, 2, and 3 always hold. They're saying if one holds, then the other ones hold. And that's really important that we realize that. So let's work out an example of this just to see how this goes. I thought we'd play a little bit. So here we go. First example. I invite you as we go along to pause the video before I make any computations and kind of see if you can see what's coming yourself. So example, let's look at just the function f of z equals z to the 4th. And so it's not too hard to see that this guy has an antiderivative. And let's go ahead and write it down. F of z equals z to the 5th over 5. And actually, this antiderivative exists everywhere. So this is, let's just say, on the entire complex plane C. And so the point is, part 1 of our theorem holds. All right, I have this function, little f, is certainly continuous, and it has an antiderivative that exists everywhere. And so now let's sort of play with the other 2 parts of the theorem. So what is that saying? Well, let's start by choosing 2 random points in the complex plane. And I'm going to, whoops, that's a bit long, but oh well. Yeah, I'll fix it. Let's pick 1 minus I. Maybe I'll use bright pink for the points. So 1 minus I. And then let's also pick, let's call this one Z1. So Z1 is, sorry, not 1 minus I, minus 1 minus I. Minus 1 minus I. And Z2 is 5 plus 2I. So 1, 2, 3, 4, 5, 2I. So here's Z2 equals 5 plus 2I. And now I want to draw some random contour between them. Let's do this one. Okay, and I'm going to go that way. I'm going to go from Z1 to Z2. And let's call this contour C, and I'd like us to work out the integral over C of z to the 4th dz. And so the idea is, in general, when you're doing a contour integral, you need to parameterize C, and then you plug the parameterization in times the derivative. of the parameterization and work it out. But I don't have a formula for C. I just made this up. But let's use our theorem. The theorem says, hey, you have an antiderivative. You can just plug in the endpoints. So I don't need to parameterize C. This is equal to z to the 5th over 5 evaluated at -1 minus I, 5 plus 2I. And so this is just a Calc 1 problem. You plug in 5 plus 2I, take it to the 5th power, divide by 5, subtract, plugging in -1 minus I. I'll spare you the computational details, but you should end up with negative 1,479 plus 4,278 I all times the 5th. So the point is I don't need to parameterize C. And here's the other fun point is I can have a different parameterization of C. Here's another one. And it's the same thing. It doesn't matter how you parameterize C. And in fact, I didn't say anything about whether it was simple or not. Quite literally, any path that takes you from here over to there, you're going to get this value as your integral when you integrate z to the 4th. Similarly, any path taking you from z1 to z2 is going to give you this value. Let's pick a closed path now. So let's let C be any closed path in the complex plane. Maybe I've got a path that looks something like this. Who knows? I'm going to go that way. And the point is the integral over C of z to the 4th dz. I don't even need to plug in any endpoints. I know that when I do, I'm just going to get 0 by our theorem. So that's the power of this result. However, it's limited in the sense that you need to know what the antiderivative is and be able to compute it. So let's just go back one more time. I have a continuous function. F is continuous. I'm integrating a continuous function on a domain D, right? And I can, if I have an antiderivative of my little function, then I can use that antiderivative to evaluate contour integrals. So that's our first result. Let's do another problem just to play with this theorem and sort of get at what this theorem is really saying. So next example, let me see here. Example, let's do, I'll say consider f of z equals 1 over z to the 4th. All right, well, you should realize this function is not continuous on the entire complex plane, but it is continuous on, let's call the region, the domain D. D here is just the complex plane. Subtract 0. This is really the set of z such that the modulus of z is positive. All right, and it has an antiderivative, f of z, big F of z, equals negative 1 over 3z cubed on D. So again, I can use my theorem, and let's convince ourselves that this region is a domain, right? Let's sketch it. We're just taking everything except the origin is in my domain D. And so let's think about it, right? This needs to be non-empty, clearly non-empty. Needs to be open. It's an open set. Although the way that I drew the hole might suggest it's closed, but it's an open set and it's connected. All right, so let's do an example integral then. So let's take the contour integral. Occur a circle, any radius you like, centered at 0. And I want to integrate 1 over z to the 4th over that curve. And so let's think carefully about this. So let's go back and look at our theorem. Can I apply it here? This function has a discontinuity inside the curve. Let's go back and look at it. So what does it say? It says f is continuous on a domain D. Well, f is certainly continuous on C, get rid of 0. And it has an antiderivative on C, get rid of 0. And so as long as I pick points in the domain, meaning non-zero, then any path from my point to my point, z1 to z2, I can use the antiderivative to evaluate. So the point is I'm good to go. Even though there's this problem point here at the origin, I can still apply the theorem, and actually this curve is closed, and so I'm just going to get 0 for the answer. So I'll leave you with a question to think about if you have time. It's not essential, but it's certainly a good thing to ponder. So can we evaluate this integral the same way? Will similar techniques work? And so I leave you to figure out whether the answer to that question is yes or no, and I'll stop